Hi guys, welcome to my YouTube channel Physics Springs. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help you to crack the exams related to physical science. Okay. So guys, this is the lecture number uh, second of the thermodynamics and statistical physics. Okay. So guys, before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, so well, let's get started. Okay, so first we are going to study that specific heat for liquid and solid. Okay, so specific heat for liquid and solid, and then we'll study for gas. Okay, solid, which is denoted by S. Okay, specific heat for liquid and solid. Specific heat for liquid and solid. And this we know, right? This is Q. We know the formula Q equal to ms delta T. Ms delta T. Q equal to ms delta T. Q equal to ms delta T. Okay, so from here S, this is the specific heat for liquid and solid. Okay, S is going to be Q upon uh, m delta T. Okay, m delta T. Right. So from here, if m equal to 1 kg and delta T equal to 1 degree Celsius, right? 1 degree Celsius. That implies uh, Q S is going to be equal to Q. Okay, then S is equal to Q. Okay, so this is S is the specific heat for liquid and solid. Okay, this is Q equal to ms delta T. Okay, so S equal to Q upon m delta T. Okay, so this is for liquid and solid. Now for gas. Okay, specific heat for gas. Specific heat for gases. Okay, specific heat for gases. So for gases we have Q equal to Q is NC delta NCDT, guys. Okay, NCDT, where N is equal to number of moles. N is equal to number of moles. C is specific heat. Okay, and that depends on the way the heat is supplied. Oh, okay, so depends on the way of heat supply. Okay, so C is specific heat that depends on the way of heat supplied. Yeah, the way we have supplied the heat. Okay, that depends. Okay, so important formula, guys. This is okay. Q equal to NCDT. Okay, for the specific for gases. Okay, so from here we can get C equal to uh, Q upon NDT. Okay, and if N equal to 1 mole and dt equal to 1 Kelvin, in that case C is going to be equal to Q. Okay, or we can write this, that the amount of heat amount of heat given to the system to raise the temperature raise the temperature of 1 mole gas 1 mole of gas by 1 Kelvin. Okay, this is the definition, guys. Okay, so C equal to Q means the amount of heat given to the system to raise the temperature of 1 mole of gas by 1 Kelvin. Okay, so these are simple things which we have already studied. Okay, and now that zeroth law of thermodynamics. Okay, zeroth law of thermodynamics. What zeroth law of thermodynamics says, guys? Okay, zeroth law of thermodynamics says that suppose this is A, this is B. These two systems A and B are in thermal equilibrium with system C. Okay, this system C. So these are in thermal equilibrium with system C. Two system A and B are in thermal equilibrium with system C. Then A and B are also thermal equilibrium with each other. Okay, so that is what zeroth law of thermodynamics says. Okay, if two systems are in thermal equilibrium with third system, okay, then these two systems are also in thermal equilibrium with each other. Okay, so this is the zeroth law of thermodynamics. Very simple. Okay, next is first law of thermodynamics, guys. Okay, first law of thermodynamics. First law of thermodynamics. Okay, what it says. But before that, I'll tell you two things. That is state variable and path variable. Okay, state variable, okay, and path variable. So what is state variable? That is which doesn't which is independent of path, which that does not depend on the path, right? That is, for example, state variable is U, internal energy. Okay, so it depends on the final and initial and final state. So it doesn't depend on the path. It is independent of the path. Okay, so suppose this is the initial state and this is the final state, okay, of the system. So whether it is go from this path or this path or this path, that doesn't matter. It only depends on initial position of the system and final position of the system. Okay, so this is path independent. State variables are path independent. Okay, so path independent. These are path independent. Okay, now second is path variable. Okay, path variables, path variables. Okay, path variables means which depend on the path of the path, right? And they depend on the path, not final and initial state. Okay, so what the path variables are? Delta Q. Okay, we'll write like delta Q and delta W, work done and heat supplied. Okay, so heat and work, Q and W, right? These are path dependent, path dependent variables. Okay, so if it's initial position, it's final position of the system. Okay, so if you go with this path, if you go with this path, if you go with this path, so it will depend on the path. Okay, okay, very simple, guys. I hope you have understood. Okay, next is the first law of thermodynamics. I'm going to write. Okay, okay, so this is any system, guys. Okay, I'm explaining first law of thermodynamics. Okay, this is any system. Okay, this is gaseous system, guys. Okay, and what we have done is we have given del q heat. Okay, and that system, and del w work is done on the system. Okay, and remaining energy is used to increase the internal energy. Okay, so internal energy, that is du, or u. Okay, so this is a system. We have given del q heat. So by giving, because we have given del q, so del w work is done, and remaining energy is used to increase the internal energy of the system. Okay, so how we are going to write it mathematically, that is going to be del q is going to be equal to du plus del w. Okay, so this is the first law of thermodynamics. First law of thermodynamics. First law of thermodynamics. Okay, so this is a system. We have given del q heat. So del w is work done on the system. Okay, and remaining energy is used to increase the internal energy of the system. So del q equal to du plus del w, because these are we have denoted del q and del w, right, by del, because that shows they are part dependent function, part dependent variable, and del u is that doesn't depend on path. Okay, the state variable, and that's why we have denoted value by du, that internal energy by du. Okay, well, so now work done, that is delta w, is, we know, that is pdv. Okay, pdv, and that is pdv is area under pv curve. Okay, area under pv curve, area under pv curve. Okay, now internal energy. Okay, internal energy, very important. Internal energy. Okay, internal energy u is equal to f by 2 nRT. Okay, where f is degree of freedom. I have explained degree of freedom in my previous lecture. Okay, where f is DOF, that is degree of freedom. Degree of freedom. Okay, f is degree of freedom. F is degree of freedom. Okay, very important formula, guys, you need to note down. Okay, u equal to f by 2 nRT. Okay, f is the degree of freedom, n is the number of mole. Okay, f by 2 nRT. Okay, so and where, and r is gas constant, and that value is, we know, that is 8.314. Okay, joule per mole Kelvin. Joule per mole Kelvin. Okay, that is the value of r, that is gas constant. Okay, okay, and from here you can see the internal energy u is proportional to T, right? Very important. Means if we if we increase the temperature of the system, its internal energy will increase. Okay, so that linearly proportional to the temperature. Okay, very important. That means if we increase the temperature of the system, that implies internal energy du will be increased. Okay, and if we decrease the temperature of the system, that implies uh, du will also decrease, because u is proportional to temperature. Very important one. Okay, this formula is also very important. F by u equal to f by 2 nRT. Okay, next is ideal gas. Okay, so we'll talk about ideal gas. So we know ideal gas. Ideal gas. So ideal gas means this is the gas in the system. Okay, so these are the ideal gas. Okay, ideal gas means the particles of ideal gas or the molecules of ideal gas are non-interacting. Okay, they are not. They don't interact with each other. Okay, non-interacting. They are non-interacting. Okay, they are non-interacting. It means because they are non-interacting means their potential energy is zero. Okay, P, that is potential energy. So this means the molecules of ideal gas or the particles of ideal gas has zero potential energy. Means they only possess kinetic energy. Okay, right? So means they have only kinetic energy. Kinetic energy which is equal to half mv square. Okay. Next point. The perfectly elastic collision. Okay, so they collide with each other, and the collision is perfectly elastic. Okay, so perfectly elastic collision, elastic, perfectly elastic collision, perfectly elastic collision. Okay, between the this one. Okay, okay. Next point is all molecules are spherical and identical. Okay, all molecules are spherical in shape. Okay, molecules are spherical. These are the qualities of the particles or molecules of ideal gas. Okay, so all particles are spherical and identical. And identical. Okay. Next, an ideal gas equation is, we know that is PV equal to nRT. PV equal to nRT, that is the ideal gas equation. I have also explained this in my previous lecture. Okay, so n is number of mole, R is a gas constant, T is temperature, P is pressure, and V is volume. Right? Okay. Well, now next is that CV. That is molar specific heat at constant volume. Okay, molar specific heat, molar specific heat at constant volume, at constant volume. Okay, molar specific heat at constant volume, guys. Okay, so that is this one. So V equal to constant, right? This implies dV equal to 0, right? So we'll use first law of thermodynamics, right? So first law of thermodynamics is del Q equal to du over del W, right? And since we know del W is PdV and dV equal to 0, so del W equal to 0, so del Q is going to be equal to du. Okay, and value of del Q we know, right? Value of del Q we know. Del Q is n CV dt, right? This one I have already explained. This one, this one. this one, Q equal to NCDT, right? So then del Q is going to be because C is constant volume, right? Specifically, so NCVDT. So this is NCVDT, guys. NCVDT, this is the value of dq, that is equal to du value I have already explained, that is this one, f by 2 nRT, right? So f by 2 nRT, and then will get cancelled, okay, and nRT dt, this is dt, okay, dt will get cancelled, okay. So this value is going to be, then value of CV is going to be, this implies value of CV is going to be f by 2 r, very important, okay, this is very important, f by 2 r, f by 2 r, where f is degree of freedom, okay, this I have already explained. Next is Cp is the molar okay, Cp is molar specific heat, molar specific heat at constant pressure, that is denoted by Cp, right? And this is going to be, guys, this is, and we'll use first law of thermodynamics, that is del Q equal to du upon del W, right? And this is going to be del Q equal to du upon del W is PdV, right? So this is the this is for that Cp, okay. Now dq values we know, that is dq is Ncp for constant pressures, Ncp dt, right? Ncp dt is going to be du value we know, right? F by 2 nRT, F by 2 nRT plus PdV, right? Now we'll use gas equation. Gas equation is simple, since we know Pv equal to nRT, right? We'll differentiate it. This is equation 1, okay. So this is going to be, we'll differentiate, this is going to be PdV plus VdP is going to be nRDT, right? Now since it is at constant pressure, means P is constant, right? P is constant, that implies dP is going to be 0. So this value is going to be 0. So means PdV value is nRT. Now we'll put value of PdV equal to nRT in equation 1. So this equation is going to be N Cp dt is equal to F by 2 nR dt equal to plus nR dt, right? Because this value is nR dt, it's nR dt. So this one, so nn will get cancelled, dt will get cancelled. So this is going to be Cp is going to be F by 2 R plus R. Okay, this is important formula. Cv is F by 2 R and Cp equal to F by 2 R plus R, right? This is Cv. Okay. Well, so this is the one. Now, so from here we can find value of Cp, or we can write Cp is going to be like this one. R we can take common, or this is going to be R if we take common. So 1 plus F by 1 plus F by 2 also we can write. Okay, this is the value of Cp. Now we'll find gamma, that is Cp upon Cv. That is called a diabatic ratio. Okay, a diabatic ratio. Gamma is called a diabatic ratio, right? So gamma is the value is going to be this one. This is going to be Cp upon Cv. Cp value is this one, R into, or I'll write like this, F by 2 R plus R upon F by 2 R. Okay, R will get cancelled, so this is going to be 1 plus F by 2 upon F by 2. Okay, so we'll solve it. So this is going to be 2 by F plus 1. Okay, or 1 plus 2 by F, or we can write F plus 2 upon F. Okay, same thing. Very important one, guys. You need to know down. Very important value of gamma. This is 2 by F plus 1 or F plus 2, F plus 2 upon F. Okay, F plus 2 upon F. Next point. Next point is so now for monoatomic gas, we will find the value of gamma. Okay, monoatomic gas, monoatomic gas. For monoatomic gas, okay, I'm going to find the value of this. For monoatomic gas, we know, guys, degree of freedom F equal to 3. I have already explained. Okay, so now CV is going to be F by 2 R, right? So this is 3 by 2 R, and Cp is going to be F by 2 R plus R, right? So that is going to be 3 by 2 R plus R, right? That is 5 by 2 R, right? Now the value of Cp upon Cv, that is gamma, is going to be 5 by 2 R upon 3 by 2 R, right? This will get cancelled, 2 will get cancelled, R will get cancelled, 5 by 3, and this value is going to be 1.66. This is the value of gamma, okay, for monoatomic gas. Very important value of gamma. It is asked in questions, okay. Next is for diatomic, for diatomic, for diatomic, we know degree of freedom is 5 at normal temperature, right? 3 for that translational degree of freedom, and 2 are rotational, right? So for that, we know that this one CV is going to be F by 2 R, means 5 by 2 R. Okay, F is 5, right? And CP is going to be F by 2 R plus R. Okay, so this is going to be 5 by 2 R plus R, means 7 by 2 R, right? Then gamma value is going to be Cp upon Cv, and that is 7 by 2 R upon 5 by 2 R. R will get cancelled, 2 will get cancelled, 7 by 5, and this value is going to be 1.4. Okay. Now for this also you need to note down, for polyatomic gases, polyatomic gases, value of gamma is 1.33, guys. Okay, this you need to note down. Very important. For polyatomic gases, gamma value is going to be 1.33. Okay, there is one question which is asked in CSIR net. I'm going to solve. Okay, this question is asked in CSIR net. Okay, and question is, we need to find Cp upon Cv, that is gamma. Okay, for monoatomic gas, for a monoatomic gas in 2D. Okay, for 2D degree of freedom for monoatomic gas, in we know, right, for F equal to, we know F equal to 2 for monoatomic gas in 2D, right? We know in 2D uh, degree of freedom F equal to 2, right? So Cp is going to be simple F by 2 R plus R, and that is going to be 2 by 2 R plus R, right? So this is 2R. Now Cv is going to be F by 2 R, means 2 by 2 R, that is R. This implies Cp upon Cv. Look how simple this question is. It is asked in NET, okay? Cp upon Cv is going to be 2R upon R, that is R. My apologies, this is 2. So 2 is the answer, guys. For 2, okay? 2 is the answer. 2 is the answer. Okay. Next is, now we know, guys, since we know del Q equal to du plus del W, okay? This we know, this is the first law of thermodynamics, okay? And del Q value is NCP, dt we know, and du values we have already got, right? NCV dt, and dW value also we know, NR dt. I have already explained NR dt, right? NR dt, NR dt, right? So from here we can get this will get cancelled, and NTT will get cancelled. Cp is going to be Cv plus R, or we can write Cp minus Cv is R. Very important formula. This is called Mayer's relation, okay, for ideal gas. Mayer's relation for an ideal gas, okay. So this is Mayer's relation for an ideal gas, okay. Now there are 2 points, very important points I am going to write. The first point is the heat supplied, the heat supplied to the system, at constant volume, at constant volume. If we have supplied heat at constant volume, that implies dW equal to 0, because dW equal to PdV, right? dV equal to 0. Second point, complete heat changes in this case, okay. Because in this case dW equal to 0, then du equal to del Q equal to dW, right? This means complete heat changes the internal energy. Complete heat changes the internal energy, right? Internal energy of the system. Okay. So implies T increases fastly. Okay. Next is at constant pressure, heat is used in both work done and change in internal energy. Okay, so at constant pressure, heat is used in both work done and change in internal energy at constant pressure. So this implies Cp is greater than Cv. Okay, or we can write gamma value is going to be Cp upon Cv, and that value is going to be, that we know, right, f plus 2 upon f, right? Or from here we can get value of f, that is going to be 2 upon gamma minus 1. Okay, so from here Cp value we can write in terms of f is f by 2 r, or in terms of gamma this is going to be r upon gamma minus 1. Similarly, value of Cv is we know f by 2 r plus r, that implies in terms of gamma this value is going to be f plus 2 upon 2. Okay, or we can write in terms of gamma r upon gamma minus 1. Okay, so this is okay guys. So before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, okay guys, so thank you so much guys. Bye now.